All right, let's dive into one of computer science's most foundational data structures, but one that you might not use every day in Python, the linked list.
So let's just get right to it with the big question. I mean, we all know and love Python's built in list, right? It's powerful, it's flexible, it's usually pretty fast. So, why on earth would you ever need to bother with something else, like a linked list? Well, the answer, like with so many things in programming, really comes down to performance. Let's think about one specific scenario. What happens when you need to add something to the very beginning of a really big collection? If you're using a standard Python list, the computer has to shift every single existing element one spot over to make room. A linked list, though, it handles this in a totally different and frankly, brilliant way. And when I say differently, what I really mean is incredibly efficiently. A linked list can add an element to the front in what we call constant time, or O of 1. Just think about that for a second. The time it takes is always the same, a constant, whether your list has 10 items or 10 million. It doesn't get slower as it gets bigger. So how is that even possible? To get how that works, we've got to pop the hood and look at the anatomy of a linked list. It all starts with its basic building block. So the real magic here is in the structure. A Python list is basically one big, continuous block of memory. A linked list, not at all. It's made up of these individual, separate objects called nodes. And each node is just a simple little package holding two things: the piece of data you actually want to store and a pointer, basically a reference to the next node in the chain. And this picture here shows it perfectly. You've got a head, which is just our entry point to the list. It points to the very first node. That node holds some data and points to the next one, which points to the next one, and so on. The whole chain finally ends when a node's next pointer points to nothing at all, or null. It's a sequence connected by these links, not by being neighbors in memory. You know what's wild? This whole powerful idea boils down to this incredibly simple piece of Python code. That's it, a simple class and a init method to hold our data, and then two properties, one for the data itself and one for that crucial next pointer, which we just set to none to start. Okay, so now that we get the structure, let's see how it pulls off that O of 1 magic trick when we add an element to the front. This is really the art of insertion. See, the key is we're not shifting anything. It's more like a quick three-step dance. Step 1, you create your new node with the data you want to add. Step 2, you tell this new node's next pointer to aim at whatever is currently the head of the list. And finally, step 3, you just update the main head of the list to be your new node. And that's it. You're done. No big reshuffle, just a quick rewiring of a couple of pointers. All right, you ready for a bit of a brain teaser? This is a classic problem you'll see all the time in coding interviews because it really tests if you understand this pointer-based thinking, reversing a linked list. The tricky part is you can't just slice it backwards like a Python list. You have to do it in place by just manipulating the pointers. And the whole secret to pulling it off is this careful juggle of 3 temporary variables as you walk down the list. One to remember the previous node, one for the current node you're on, and one to hold on to the next node so you don't lose your spot. And this is the core logic right here. Inside a loop, you first stash the next node in a variable so you don't lose the rest of the chain. Then, and this is the big move, you reverse the pointer. The current node's next now points backwards to previous. After that, you just inch everything forward one step. Previous becomes current, and current becomes that next node you saved at the beginning. You just do that over and over until the whole chain is flipped. Pretty neat, huh? So let's bring it all together. When should you actually use a linked list instead of a regular Python list? It's never about one being better than the other. It's about using the right tool for the job. Time for the final showdown. This table is basically your cheat sheet. It lays out all the trade-offs perfectly. If you need to grab an element by its index, say the 500th element, a Python list is king. That's an O of 1, constant time operation. A linked list is awful at this. You have to walk the whole chain from the very beginning. But, and this is the big but, when it comes to inserting or deleting from the start of the list, the roles are completely reversed. The linked list is O of 1, lightning fast, and the Python list is O of n, which means it gets slower and slower as the list gets bigger. And this quote from the folks at Real Python just hits the nail on the head. Linked lists really shine when you're building a queue, a first-in, first-out system. The best analogy is a line at a coffee shop. People are always being added to the back of the line and served from the front. That constant adding and removing from the ends is the perfect job for a linked list.
So I'll leave you with this to think about. Now that you understand the very specific, very powerful advantages of a linked list, where in your next project could it be that secret weapon that gives you a massive efficiency boost?